Okay, so at the end of the previous presentation for this chapter, I think we finished with this slide. So just to review, so what we found out was that, if you have the individual x values, it could have a distribution not necessarily normal. Like in this case you have x, which x values to be um, skewed to the left, in fact, and it is not a normal distribution, and the mean was 173. These details were given in the previous slide. And then if you take samples of size n equal to 10, and they do the histogram for the sample means, this is the histogram for the sample means, you can see a big change in the shape. The shape turned out to be bell curve, like a bell curve, with the same mean, and also the standard deviation, or the spread, actually the spread getting really reduced. Okay, so now standard deviation is the measure of spread. So what this is telling is that, okay, for the mean value, the standard deviation is much less than the mean value for the individual x values. Okay, so we have learned three things in here. Okay, I think we need to change this to 2. Wonder why it happened. It's 2. Okay. So now let's go to the next slide, and sort of see the summary of all these results. So actually finding one is a central limit theorem we talked about in the previous presentation. So what it says is that regardless of the probability distribution of x, x bar will have a normal distribution as long as the sample size is large enough, and the sample size should be, for it's effective for more than 25. Okay, so in fact, maybe let me write it in here. So n can be greater than or equal to 25. Okay. Um, Let me make it. Yeah. All right. So that's what the central limit theorem is saying. Central limit theorem talks about the shape of the distribution. Like if you have sample size to be more than or equal to 25 for practical purposes, the mean will have a normal distribution. Now, what is the mean for that normal distribution? It is the same as the mean for the individual x values, and notationally it is mu. Now, this property, that mean of the sample mean is the same as the mean of the individual x, is called unbiasedness. Okay, you need not worry too much about this for this class, but if you do a more advanced stat class, you may come across that term. Okay, now the third one says that the standard deviation of the mean is equal to sigma over square root of n is the sample size. So even from this formula, you can see that as you keep increasing the sample size, you can get the standard deviation of the sample mean to be reducing, quite drastically. Okay, and that is something good, because lesser the spread is, data is more reliable. So which means what this is telling is that if you have a sample mean, the data coming from a sample mean, or information coming from a sample mean, is much more reliable than information that you get from one single x, which is obviously making sense. And even the sample mean, if you take, the sample mean based on 30 observations, may not be as good as a sample mean based on 100 observations. As you increase, and the reliability of the information that you get from that sample mean will be more. Again, it makes sense, right? Okay, so these three properties are very important. Actually, in fact, okay, let me also point out something. Now we have been talking about standard deviation. Now, standard deviation is the measure of the spread, and that, this term is used when we talk about individual x, a random variable. Now, when we talk about the standard deviation of a statistic, such as the sample mean, you will not use the term deviation, you will use the term standard error. So that's what this is saying. The standard deviation of the sampling distribution of the mean has a special name, standard error of the mean. So instead of deviation, the term word deviation is replaced by error when you talk about the standard deviation of the mean. Okay. So now, actually sigma x bar, which is the standard deviation of the mean, is actually standard error of the mean. It's just something clear about terminology. Okay, and the formula remains the same, sigma over square root n. Okay, all right. So let's go to the next slide. So here in this slide we talked about standard error. Okay, now here's an example where we apply that result of square root law. Okay, so if you have n equal to 1, n equal to 1 means just one single observation. Standard error of x bar is the same as the actual standard deviation, right? If you have n equals 4, that means this is based on, the sample mean is based on 4 observations. Standard error of x bar is sigma over square root n, and when you do the math you get 7.5. For n equals 16, you will get 3.75. You can see that as you increase n, standard deviation decreases. See, from n equal to 1 to n equal to 16, the deviation, standard deviation or standard error of the mean, right, has decreased drastically, which is really good news. Okay, all right then. Let's go to the next. Okay, so now putting it all together, remember the notation, this abbreviation STM, that stands for sampling distribution of the mean, right? So the sampling distribution of the mean is notationally this. Sampling mean is x bar is normal with the same mean mu of the individual x with a standard error. Okay, now how do you find this standard error? Right here, sigma over square root n. See, this symbol does not go inside, so that's why I had to write it like this. So this standard error is right here, sigma over square root n. Okay. So here again we are writing this, the sampling distribution of x bar is normal, right, with mean mu, right, and standard error to be sigma over square root n. Okay. Of course, when the sample size is large, or also if you start with a individual x to be normal, in that case, even if n is not large, still x bar will be normal. Okay, so that's what this is saying. Okay, so now using this information, we can make inferences about the mean. Okay, actually, now we have a normal random variable. So we can go back to, in fact, chapter 7, where we talked about normal distributions, and we can find probabilities. Okay, so and then we can use the empirical rule, like in here. See, 68% of the sample mean will be mu plus or minus 1 standard error, and then you can find things like this. So anything that applies to a normal random variable will apply to the sample mean. That's very convenient because we know lots of stuff about normal random variable, and we studied in this class, in chapter 6, right after the binomial chapter. Okay, all right, let's go here. So look in a picture. We can see now this is the population distribution. See, this is like the distribution for individual x. Okay, that is like sampling distribution with n equal to 1. So that means it is like a trivial case where the sample mean is based on only one observation. So those are individual observations. Okay, so here you have sigma to be 15. Remember, we calculated it. And if you take n equal to 16, we realize that standard error of the mean, same as standard deviation of the mean, turned out to be 4.7. Just look how thin this curve is. You have the same mean, okay, but the standard deviation is so much less when you take a sample mean with 16 observations compared to just individual observations here. Okay, So now this distribution, this tall distribution, which is actually the sampling distribution for x bar with n equal to 6, that gives you much more reliable information about the mean than the individual distribution. Okay, so it's much better to work with x bar with n equal to 16 than x with n equal to 1, right? So that's what it is saying. Now actually, if you increase sample size from 16 to 100, you can kind of expect this curve to be really, really skinny. And that means almost all the information is, no matter what sample you take, almost all the time it will be right around 100. So that will be so more reliable, right? Okay, so let's go to the next one. Okay, now here we talk about another rule in statistics, law of large numbers. Now what this tells is, again, this is also like, proposing to increase the sample size. If you have a sample size to be large, then the sample mean value will get closer and closer to the actual mean. So larger the sample size is, sample mean will be closer and closer to the mean mu. Okay. Now this tendency is called the law of large numbers. That means, the sample mean tends to the population mean as n tends to infinity, if you think in terms of calculus. Okay, all right. Now this is illustrated in the next slide. Let's see here. So now here sample size n is on the horizontal axis. Now see, we are getting the data from x, which had a mean of 173. Remember, and then if you take n equal to 5, sample size of 5, what you expect the sample size the sample size to be about is about, not the sample size, the sample mean to be, to be sort of fluctuating. See, but as you keep on increasing the sample size to thousands and even 10,000s, it's getting really close to the actual mean mu, which is 173 in this case. And you can see how stable it's getting if you, of course, have into the really large 10,000. Now it looks to be from this picture that for law of large numbers to work, n has to be really, really large. But central limit theorem, remember, for all practical purposes, we know that, n more than or equal to 25 is good enough. Now that's a big plus for practical applications when it comes to central limit theorem. Okay. Okay. Okay, so now in this, now this is section 8.3. Now in here, we are sort of switching now to the counts and proportions. Remember in chapter 6, we talked about binomial distribution and the number of successors. Now, what is the sampling behavior of that? Because even there you have a sample. You will take n trials, and that means sample size of n. And in that trial, you will have either successes or failures. So that would be like binary data, right? Zeros or ones. And you will count the number of successes. Nevertheless, number of successes, if you want to call it x, now that is a statistic, which is in fact a random variable. Okay. And then it is binomially distributed. And if it is a binomial distribution, what are the parameters n and p, right? Now, since this is a statistic, we can talk about the sampling distribution of it, which is the same as binomial with n and p. And for a specific example, if n equals 10 and p equals 0.2, that means the probability of success is 20%. And you have repeated the experiment 10 times, right? And then, you will have the sampling distribution to be like this. Now, also something new, when you talk about the sampling distribution related to binomial counts, sometimes you talk in terms of the number of successes. Sometimes you talk about the sample proportion of successes. So in fact, p hat is the notation for sample proportion. So if you talk about p hat, the sample proportion, now that will have a mean of mu, mean of mu, which is actually zero point 0.2 because we are talking about proportions. If you talk in terms of counts, then the mean will turn out to be n times p. Remember, with the binomial case, when you have n times p worked out here, that will be 2. So it's either np if you're talking in terms of counts, or the p itself if you're talking in terms of the sample proportion. Okay? All right, so let's go to the next slide. So now you can see the connection, or actually the similarity, or the one-to-one correspondence between the number of successors and the sample proportion, when it comes to looking at the histogram. Okay, the probabilities are the same, right? So, and then see for any given success, there is the corresponding proportion, and the mean for successes will be 2, and for proportion it will be 0.2. Okay, so so these, when you talk about binomial situations, you can either talk in terms of number of successes or number of proportions. Okay, now here we talk about number of successes or even sample proportions. We talk in terms of the binomial distribution. Now again, because of the central limit theorem, see, when n is large, even a binomial distribution will turn to be a normal distribution if we are working with the mean. Okay, remember, that's what the central limit theorem is saying. Sample mean is normal no matter what the distribution of x is, provided n is large enough. So because of that, there is something called a normal approximation to the binomial distribution. So that is what this slide is about. So when n is large, the binomial distribution takes on normal properties. Now, how large does the sample have to be? If you have NPQ, if you multiply these three quantities together and it is more than or equal to 5, then you can approximate the binomial by a normal. Okay? All right, so that's all you got to check, just to see if if the approximation works well. Just see if n times p times q is more than or equal to 5, and then you can approximate a binomial with a normal. Soon we will see how it applies. In fact, let's see how npq works out here. If you have if you have n equals 10, p equals 0.2, and then q will be of course 0.8. Then remember, q is 1 minus 0.2, and if you multiply all these three together, you will get npq to be 1.6. Okay, so now this is too small to apply the normal approximation. Now on the other hand, if you take n to be 100, p to be 0.2, q will be still 0.8, then npq will be 16. If you have n to be 100, that means if you have repeated the trial 100 times, right, then you can apply the normal approximation. Okay, all right then. So let's go to the next slide. So you can see that, now look, when n equal to 10, remember the approximation wasn't good because npq was like 1.6. You can see when you do the histogram for the binomial with n equal to 10 and p equal to 0.2, you don't get a nice symmetric bell curve. On the other hand, if you increase the n from 10 to 100 with the same p, npq, remember, turned out to be 16. What a nice bell curve you get. So you will get the normal approximation if npq is large enough. Okay, and one way to make npq large enough is by increasing the n, as we saw in this example. Okay. Okay, so now here's the theory part. I mean, theory means practically useful theory part for normal approximation for a binomial count. For a binomial count, mean is NP, we know that. Count means number of successors, right? And sigma is square root of NPQ. So now, when the normal approximation applies, we will say, okay, x, which is the number of counts, is normal with mean mu, NP, standard deviation square root of NPQ. It's really, really simple. You will get the mu and the sigma, which are the parameters for a normal distribution, using these formulas. That's all. Okay. All right, so I'm just waiting just for about 10 minutes. Not, I'm sorry, not 10 minutes, 10 seconds. So that, okay, so this slide is, now remember we talked about, we can talk about either sample count or sample proportion. Now, instead, if you talk about sample proportion, mu will turn out to be p. Remember, in that practical example, mu was 0.2 for the sample proportion. Remember, sample proportion I said was p hat. So that p hat notationally is like this. So the p hat, if you want to talk about binomial proportion, the p hat is normal with mean p and square root of pq over n. Okay, so it's just a matter of dividing by n and then taking the square roots, and then you will get this formula. So I mean, for this class you don't have to memorize any of these. You can have a formula sheet written. What like for the counts, this is the formula. For the proportions, this is the formula, and so forth. And then it's after that it's just a matter of working some problems. Okay, all right. So now actually look, whether it's a count or the proportion, um the normal approximation has worked very well in here. It's a nice bell curve, right? Mm. And you can see, and this is when n equals 10, I'm sorry, n equals 100. Okay, we just say n equals 100. Okay, so I think, let's see. So this, I got a little lost in here. 1 minute, please. Okay, yeah. And then, yes. Now let's go to the next slide. Yeah. So now illustrative example. Examples are really good, aren't they? So now if you have the prevalence of a risk factor in a population to be 0.2, take a simple random sample. See, I did not talk much about that. Just say take a sample of n equal to 100 from this population. Okay. Now, a variable number of cases in a sample will follow a binomial distribution with n equal to 20 and p equal to 0.2. Okay. Now, this is with n equal to 20. That's not right. I think actually this is a mistake. This should be n equal to 100. Oops. Let me go back. What happened? This should be n equal to 100. Yeah, so with n equal to 100, so number of cases will be binomial, and when you talk about a binomial distribution, you need to talk about n and p, and so that will have n equal to 100 and p equal to 0.2. Okay, now let's look at the binomial approximation. Okay, so the binomial approximation will be, I'm sorry, not the binomial, normal approximation. I'm sorry. So the normal approximation will be uh, having a mean of NP, which is 20, and a sigma of 4 by just applying this formula. So the sample count X will be normal with mean 20 and standard deviation 4. So now on the other hand, if you want to apply the normal approximation for the sample proportion, well, actually this may be, we have to stress the fact that it is the sample, certainly it is binomial, but sample proportion, then you have mu to be p, the formula for the proportion mu is p, that will be 0.2, and sigma would be square root of pq over n. Remember, in like a couple of slides before we saw this, and then it works out to be 0.04. So the p hat, the sample proportion will be also normal with different means. Here the mean is 0.2, the standard deviation is 0.04. Okay, so both the sample count and the sample proportion have normal distributions. The difference is in the mean and the standard deviation. Okay, all right. Actually, just see binomial sample count. It's better to sort of stress the fact that it is okay. So we have the normal approximation to the sample count and also the normal approximation to the sample proportion. Okay, let's go to the next slide. So now actually here's an example. Now if you have a sample with 30 cases, so you are seeing a sample of 30 cases. So now the question is, what is the probability of seeing at least 30 cases under these circumstances? So that means you have sample with 30 patients. Actually, this should have been patients. I took this from the book. Maybe I should let the author know. So suppose we have a sample with 30 patients. What is the probability of seeing at least 30 cases under the circumstances? Cases, the term cases is usually used for people with a certain condition. Okay, so what is the probability of seeing at least 30 cases? So it will be probable. This is not right. Oh, okay. I see. Okay, I made a mistake. Let me go back to the previous slide and then come back to it. Yeah. So here we figured out the normal approximation for a sample count, right? With n equal to 100 and p equal to 0.2. So the sample count has this normal distribution and sample proportion has this normal distribution. The difference is in the mean values and the standard deviation values. Okay, so now think that, okay, we have 30 100 individuals. Okay, so now let's go to the next slide. Think that, okay, we have 100 individuals. Okay, now so here now we are telling, okay, given 100 individuals, okay, then what is the probability of seeing at least 30 cases? Okay, so in other words, what is out of these 100, what's the probability that there will be at least 30 successes? Cases means, a case means a patient, a person with the disease or the person with the symptom that you are interested in. So you need to find the probability that x is more than or equal to 30. Now remember, now we are using or we are considering x to be a normal random variable with this mean and the standard deviation. We figured out these values in the previous slide, right? So now we have a normal random variable. So like in chapter 6, in the normal chapter, we can find the z-score, x minus mu over sigma. So it will be 30 minus the mean, which is 20, divided by the standard deviation, which is 4. You get 2.5. And then, you can then figure out the probability that z is more than or equal to 2.5, which is the same as this, right? Probability that x is more than or equal to 30 is the same as probability that z is more than or equal to 2.5, which you can get from the standard normal tables because z is standard normal. Go back to chapter 6, right? So let's see how it looks in the picture. So this is what you got to find. See, you have the count x's. X more than or equal to 30 is the same as proportion more than or equal to 28, and then the z-score will be more than 2.5, and then from the normal approximation you can get this to be 0.0062. You can check and see whether you get the same answer. You will first find the cumulative probability from your book, from the tables in your book, using the normal distribution or using Minitab, and then 1 minus that will give you 0.0062. Okay, all right then. So this is the end of chapter 8, and then in fact this is the last chapter for exam 2. I will post some work examples, and the probability set 2 also already will be in the website. Okay, all right, take care.